Welcome. If you're watching this, you are likely a student at Sacramento State University in either the statistics or research classes in the social work department. And if you're not, you might just be watching this to learn more about correlations, and you're welcome to do that too. So I am Professor Miles Montgomery. I am taking a look today at correlations, specifically in the context of social work, and we're going to go through this today step by step. Many of you who have had my courses before know that I try to use as many examples or metaphors or analogies as I can to explain concepts so that they're not as intimidating and that they're understandable. Today I'm going to walk through correlations in a way I like to do whenever I teach them. And the way I kind of look at it is, if you're on an airplane, there are systems that are already functioning that if they fail, there is a backup system. And if the backup system fails, the pilots are able to fly the planes manually. Well, my idea is that you really don't even want to bother with all the other systems unless you've learned something manually. So the way I teach correlations, and as I will here, is in a way where I go over the manual methods before I look at anything else. And today I'm going to be going over the manual method, but then also I'm going to show you how to calculate exactly what we do manually on Excel. I'm going to probably expand this video at some point to include SPSS as well. So I'm going to first cover manual, then move into Excel, then ultimately likely include SPSS as well. Well, let's start. So here's my preamble for correlations. If we're just starting with the basics, what we should do in terms of thinking about correlations is consider them correlations or co-arisings. The reason why we want to do this is because we're not talking about causation, even when it looks like it whenever we're studying correlations. Correlations are not causative relationships. That's the thing I usually stress in most classes I teach, and I think it's the best policy because, as usual, whenever there's a relationship, there's rarely one cause, but instead many factors. When we practice looking at change in any kind of relationship as attributable to only one cause, frequently we're practicing what we call reductionism, which is isolating one particular factor as the sole cause, which is dangerous, especially in research, especially research with people. A lot of times we can kind of propagate stereotypes by looking at only one cause instead of considering many factors. When we're looking at correlations, we are dealing with variables that are in the interval ratio levels of measurement. This is something that we always have to keep in mind. Recall that when you study chi-square analysis, the variables are exclusively in the nominal category or the level of measurement. So when we're dealing with correlations, the variables are going to be inherently in the interval ratio levels of measurement. And finally, when we're talking about correlation analysis, we're usually referring to a kind of formula called Pearson's product moment correlation coefficient, or Pearson's R for short. So anytime you see an R equals or Pearson's R equals, you know you're dealing with correlations, because that's the equation we use to find the correlative relationship among variables. Because we're talking about inferential statistics, we are also talking about a kind of statistic where we start with an examination of a null hypothesis. We did this with t-test, we did this with chi-square, and we're certainly going to be doing it with correlations as well. So again, whenever you're looking at a set of variables, and with correlations you're almost always looking at pairs of variables, which we'll get through, you do want to consider the null hypothesis first. And the null hypothesis is assuming that no relationship exists between the variables. When we are doing a correlation analysis, because we are looking at a null hypothesis, in order to determine whether we accept or reject it, we of course are going to be considering a calculated value, usually from an equation, with a critical value, which we're going to find in a textbook or some kind of a chart. Now take a look at the scatter plot I have on your right. And yes, these are called scatter plots. Notice that it has a running line. This is the horizontal line. In this particular case, that says temperature. And we have a vertical line. And in this particular case, the vertical line has a variable on it which represents sales of ice cream. So in general, we call this particular system a scatter plot. Some texts call it scattergram. I call it scatter plot. A lot of other texts do as well. Take a look at what you see on your right. You see two lines intersecting, and if you're familiar with anything that you had to do in advanced algebra, you probably recall that the vertical line is the y-axis and the horizontal line is the x-axis. And for purposes of what we're going to be doing with correlations, we want to think of the y-axis, the one that's running north and south, or climbing as I like to say. We think of that as the dependent variable, and as you might expect, the x, or the horizontal axis, we will think of as the independent variable. So I guess they go by several names, don't they? The y-axis is running north to south or climbing, and it houses the dependent variable. And the x-axis, which is running left to right, is going to be housing the independent variable of whatever study set you're looking at. Now look at this one. This is kind of a fun one. We see that in this particular example, as temperature is getting higher, so we start with 90 and we're going up to 110 on the x-axis, the independent variable, we see that the number of ice cream sales are also increasing with the heat. So, not surprisingly, people like ice cream on hotter days. We begin to see a shape take place. And by the way, this is just a reiteration of what I said before. The terms, in terms of variables, the x-axis houses the independent and the y-axis houses the dependent. You already know that. Now that's review. We locate these on scatter plots where x and y intersect. So each one of those little dots we see on the scatter plot, or plots, represents a temperature and a corresponding ice cream sale for that temperature. And again, as I noted earlier, as the temperature is rising, so do the ice cream sales, according to this chart. Take a look at what this relationship looks like. Well, it's kind of looking a little bit like a line. It's kind of looking like a line going from left to right upward. It's kind of an increase toward that ice cream cone. Doesn't that look delicious? So we have kind of a movement of the plots, if you will, from left to right going upward in kind of a line. We're going to call that a specific name here in a minute, and I've got a graph for you on that one too. Let's take a look. If you look on the far right, you're going to see something that resembles a little bit like we saw with the ice cream sales. We see the plots on the scatter plot moving from left to right and upward. We call that a positive relationship. That's where, as we see an increase in the value of the x-axis, that's of course the horizontal, we also see an increase in the values on the y-axis. Or put another way, as there is an increase in the independent variable, we also see a co-arising increase in the dependent variable. Okay? Hopefully that makes sense. Now take a look at the middle example. Now, it says negative. Well, it's going the opposite direction. You see that the plots are lining up so that instead of going from left to right upward, they're going from left to right downward. Okay? So, in other words, as the independent variable on the x-axis is rising, the dependent variable on the y-axis is falling. So that's really the definition of the negative relationship in a correlation analysis. Now, if you go over to the far left, you'll see a bunch of little dots just all over the place, just like looks like somebody spilled something. Maybe those dipping dots, who knows? It's no correlation. We really don't see a direction. So this is how we begin to decipher the data in terms of their plot points on the scatter plot. When we see the independent variable rising and the dependent variable rising as well, we call it a positive relationship. If we see the independent variable rising and the dependent variable falling, we call it a negative relationship, as stated in the center one. And then if we see dots all over the place where there's no real rhyme or reason to the way that the dots are flowing, we have no correlationship or no correlation. Okay? Hopefully that's pretty clear. Here's something to not be afraid of. This is the correlation equation. This is Pearson's R. And it looks big, doesn't it? Yeah. But really, it's not so bad, and it's pretty easy to tame if you're able to keep organized. If you keep your data in fairly organized sets, just like keeping your room clean or keeping, if you're cooking, everything kind of sequestered in their own places, it's easier to kind of balance. It's not so hard. It's just, I think it looks a little overwhelming when you first glance at it. But in the end, you find, I think, that it's not so hard. At least none of my students have complained too much about it after they understand how to sort out the data. Well, as we stated earlier, these are inferential. So because they're inferential statistics, we do need to find a calculated value. And as I tell my students, you know you found a calculated value after you did a bunch of calculations or math. So how do you find the Pearson's R calculated? You do a bunch of math, okay? Not a ton, but you do a little bit. That's how you find the calculated value for Pearson's R. Although the equation looks monstrous, it really only consists of a few values. Yeah, I mean, for example, we see that there's an n. Okay, well, n is just the number of pairs you have. Obviously, with an x and a y set of values, that you need the pair to find the plot on the scatter plot. So you're looking at the number of pairs, and you're saying, oh, okay, well, there's 7 pairs here, or there's 10 pairs here. Oh, well, that number of pairs altogether is the n value. That's usually the easiest one to find. So we already cleared out one variable right there. Excuse me, the n equals the number of pairs. Now, the sigma, which is looking kind of like the funky E, it's the Greek symbol sigma, of course, just simply means summation, sum of, and if you take a look at the numerator or the top floor of the equation below, you see that you have an n, and then you see the sigma xy. Well, that just means the number of pairs times the sum of the product, so multiplication, of x and y. Well, we'll get to that. We'll see how it's really not so bad. It doesn't look that bad after you kind of have a chance to practice it a couple times. Then when you see sigma x or sigma y, you just know that that's the value of the x and the y columns summated, or you've basically calculated all of them, added them up. That's really all that it means. Okay? And so, moving on. See if you can locate what the values are. Well, I just kind of went over that a minute ago. I just kind of showed you, the x and the y, and the x times the y. You're really only dealing with 2 columns of data, just in different ways. And again, I think after you watch this slideshow presentation, you'll have a better understanding of what this is. And it's really not that intimidating. Okay, here's a wonderful example of an application of correlation. Look at this. A study was done in which the high daily temperature and the number of traffic accidents within the city were recorded. I'm not sure what city this is, but I don't know. Maybe it's Sacramento. These sample data are shown as follows. So clearly, for each row, there is a pair of values. On the left, it's the temperature, and on the right, it's the accidents for corresponding temperatures. So if you look at the first row, 91 degrees, we found 7 accidents. Okay. The second row down, 56 degrees, we found 4 accidents. And the third row down, 75 degrees, we found 9 accidents. Well, if you run a Pearson's R calculated analysis on all of this, you're going to come up with what we call a correlation coefficient. And the correlation coefficient is a number that tells us 2 things. The direction of the relationship. Remember how we said positive and negative or no correlation? Okay, we're going to be able to discern that from the number. and then also the strength of the relationship, or how close the plots are on the scatter plot to one another. Are they concentrated really closely, or are they spread out more? Well, the number we reach from doing the calculation is going to tell us that. In any case, this is clearly looking in the sample like somebody's test question. And look at the bottom. It says, given the data, the sample correlation coefficient is, somebody ended up doing all the math. And they're asking you whether the correct answer is negative 0.57, negative 0.64, 1.54, or positive 0.57. Now, one of these answers is a total dummy answer. And after you're done with this presentation, you'll be able to look at it and just go, oh, that's... we can cross that one out right away. It's clearly not the right answer. The other three, you have to kind of think a little bit more about. And after you, of course, do the equation, you know the answer. So we'll figure out which one it is at a later time. Okay, so let's take a look again in a little more detail at the equation. Pearson's R, so anytime you see R, okay, and if you just look at the shape of this, and you forget for a minute about all of the trees, and you just kind of look at the forest, what's it look like? Well, it looks like a fraction, doesn't it? You've got that fine line that's bold in the middle. You've got a square root below it, and you've got some values within the square root, and then you've got the numerator on top. So again, numerators on top, denominators on the bottom. So I sometimes say top floor, bottom floor. So if I'm talking about the top floor, I'm talking about the numerator, what's on top. If I'm talking about the denominator, I'm talking about the bottom floor, which is, of course, what's on the bottom side of the equation. See, again, the n equals number of pairs. I went over that earlier. And then just, again, a little review. Now it's a review for you. Sigma xy is just the sum of the products of the paired scores. Okay. Sigma x is just the sum of the x scores. Sigma y is simply the sum of the y scores. Sigma x squared, well, if you take all of the x values and square them and then add them up, that's the value you would get for sigma x squared. And then sigma y squared, same thing. All of the y values squared and then added up. It's just the sum of the y squared. Again, not too difficult. Some people will say, well, it takes some time. Yeah, it does. Everything takes time. I mean, waking up takes some time. Everything's a little bit of work. So I think actually after you practice it a couple of times, it's really not as intimidating as it is when you first see it. Okay, again, I'm just going to go ahead and stick this equation up there so we just have it as a point of reference. And I'm going to talk a little bit about the information that we get from Pearson's R. I told you earlier that it gives us two specific pieces of information that are of most value to us. I said here, a great deal of information. Well, it gives important information. In one number, so once we get this equation done, it lets us know the direction of the relationship of the variables, and it lets us also know the strength of the relationship of the variables. So one number gives us all that. It also allows us to have a calculated value to compare against a critical value, which again, we'll walk through this. We're just going to take a little stroll. It's not going to be too hard. We compare and contrast the Pearson's R values, calculated and critical, and find whether or not we will, of course, because it's inferential, reject or accept the null hypothesis. Now, take a look at these. I did this on purpose so that you'd get a kind of feel of what these particular numbers mean. If you take a look at the top left example, you see that you have a scatter plot with the little plots, and below it you have a number. You have an R value that is 0.9. Well, let's take a look at this. Do you notice that just like on the ice cream sales, the plots are starting to move in a direction? They're moving from left to right and upward. So as the value on the X or independent axis is increasing, the values on the Y-axis or the dependent are also increasing. So we have a positive relationship. And not surprisingly, we also have a positive number. See that? It's 0.9. It's not negative 0.9. So for the R value, it's 0.9, not negative 0.9. All right, so that is what we would see in terms of the direction. Now let's talk about the strength. Take a look at it says 0.9. Well, when we're talking about correlations, when we go either to a -1 or a +1, we're moving toward a line that is straight. So a value of 1, r equals 1, would be a perfectly straight line where for each movement of the independent variable, you have an equal movement of the dependent variable on the y. So the closer we get to a 1, the straighter the line. And that's convenient because isn't a 1 a straight line? By contrast, if we move closer to a 0, we have less of we have less strength in the relationship. So you're going to see it more spread out or diffuse. All the little plots are going to be moving around, kind of like that. I said, somebody kind of just spilled something. So if you take a look at, again, the top left, you see that this particular r value is positive 0.9. So we know it's positive, so it's moving from left to right and up. Okay, and we also know it's 0.9, so it's going to look close to a straight line. It's not exactly a straight line because it's 0.9, not 1. And so I think that you kind of get the idea of what the positive value looks like there. Okay, let's move over to the right. Now we're in the middle column, and we're at the top. So we're on the top row, and we're in the middle column. And you see that this time we have an r value of -0.8. Well, what's different between this one and the first one? Notice that the plots on the scatter plot are moving downward this time. So they're moving from left to right downward. So as the independent variable is increasing, the dependent variable is, as the independent variable is increasing, the dependent variable is decreasing. So -0.8, okay? Negative indicates the direction of the relationship. 0.8, getting a little further away from 1, so it's more scattered than in the first example. So you can see that the closer we get to 0, the further we move from 1, the more spread out they are, whether we're talking about a positive or a negative number. It really doesn't matter. The negative and positive is just simply telling us what direction the little plots are traveling. Well, let's put a finer point on this. Let's go over to the far right column in the top row. Now we have an r value of 0.7. Now, because it's positive 0.7, there's no negative there, we know that it's moving from left to right and upward. Okay, so again, as the independent variable is rising, so is the dependent variable. Now this time it's 0.7. The first one was 0.9. Do you notice that between the first example we looked at and this one, 0.7, the dots are starting to spread out a little bit more? Well, not surprising. The further we move from 1 and the closer we move to 0, we are seeing more spread or diffusion. Okay? Well, if we look at the middle row, we can see again, as those numbers, either positive or negative, are getting further from 1, those dots are spreading out. We still get a sense of the direction, but we also know that the strength of these is lessening as the values are moving closer to 0. All right. Now look at the bottom ones. I mean, you're seeing less and less of a correlation here. You're starting to see where the closer we get to 0 again, it just starts spreading out and it's losing direction, and it's harder to tell whether it's even positive or negative. Kind of get a little bit of a sense, but it's difficult. So again, Pearson's R is giving us two vital pieces of information with regard to correlations. The positive or negative value is letting us know whether or not the line is traveling from left to right upward or from left to right downward. And the decimal, after the number that follows the decimal, whether it's closer to 1 or to 0, is going to tell us the strength of the scatter plots, or how closely or densely they are together or spread out. All right? Hopefully that makes some sense. Just to put a finer point on this one, I have something here that's a little bit of a helpful chart. Notice that whether we're talking about a negative correlation or a positive correlation, pretty much as far as you can go is a 1. Do you see that? On the far left and the far right is a 1. So whether it's a -1 or a +1, that's as far as you can go. The negative and positive, again, is just indicating which direction the plots are flowing, downward or upward. In the middle, of course, is 0, and that indicates a weak relationship where everything's spread out again. So remember when we were looking at that example a few minutes ago about the trick question? I said which one of these is just the throwaway? You can just glance at the answer choices and say, oh, yeah, we can get rid of that one right away. Yeah, that was the 1.54, because with a correlation coefficient, you're not going to get any farther than a 1, positive or negative. So that's a great trick question for somebody who's testing on correlations, is give the students a value of higher than 1, either negative or positive. If you have a negative 1.54 or a positive 1.54, it's kind of a nonsense number, because as far as you can go one way or the other is a 1. So anytime you see that, you can kind of be resting assured that it is not the correct answer. It's just not there if you're dealing with correlation coefficients. Okay. All right, let's take a look at the next slide. Well, I started to go ahead and give you an example. And in fact, this is the example you recognized from earlier with the temperature and the accidents. Notice that what I've done here is I've scripted out in columns and rows the values we saw on the chart earlier. On the left-hand side, the x, or independent variable, we have those temperatures, 91, 56, 75, 68. And then we have in the y column, the number of accidents, the corresponding number for each temperature of accidents. So at 91, we see 7. 56, we see 4. We saw this before, so it shouldn't be unfamiliar to you. Do you recall that when we looked at the equation for Pearson's R, that one of the values I pointed out was sigma xy? Well, sigma xy, of course, is the sum of x times y. So what did I build into this already? I built in a column on the far right of xy. I did this so that you can train your eyes to look across the data. And so if we start with the top row, 91 times 7 equals 637. Okay. 56 times 4 equals 224. Do you see how I did that? Well, I did that on purpose so that you don't get too confused or overwhelmed with all the data on the page. This is the way I have my students do this type of equation, because it just helps keep everything really organized. And when you can keep it organized, it's much less intimidating. So again, x values, y values, x, y. Obviously, we're going to end up adding up all of these columns when we do the third pass of the data. So this is just the first pass. The first pass is where I write out, or I have my students write out, the x values, the y values, and then multiply across to find the xy column, leaving a space in between each. Just helps keep everything organized, and you're going to see why on the next slide. Okay, once we've done the x and y values, then in those blank spaces we had in between, we will do the x squared and the y squared values. So if you look on the far left again, we see that 91 is in the first row, the first temperature we looked at. Well, 91 times 91, or 91 squared, is 8,281. So I put that there. And then if you continue over, 7 is the number of accidents we saw. Well, we're going to need that y squared value eventually, so go ahead and multiply 7 times 7, or 7 squared is 49. So the way you do this, the order of operations for calculating these numbers, is not real hard once you set up the values the way I've done. So your x column, your y column, your xy column. Then the second pass, you do the x squared and then the y squared. And then with the third pass, if you kind of gathered how I did this already, go ahead and on the next slide, you just total them all up. So if I added an extra row at the bottom, you can see that I have underneath the x column now the sigma x, which again I just added 91, 56, 75, 68, added them all up, and I got a total of sigma x equals 477. Okay, same thing for x squared column. I found 8,281 plus 3,136, added them all up, got a pretty large number at the bottom. So the sigma of x squared is 35,291. Okay, I did the same exact process for y squared column and the xy. So now I've got sigmas for each and every one of these. So if you look at the equation on the bottom, the Pearson's R equation, we already know what the n is because there's 7 pairs of these particular numbers. The n is just simply the number of pairs. So the first pair, 91 and 7, the second pair, 56 and 4. Okay, there ends up being 7 altogether. Okay, so we put anywhere we see an n on that equation down there. It's just like stacking books on a shelf. Anywhere we see the n, we just put a 7. Okay, and I've done that on the right. So if you're looking at the equation on the left, you'll see the abstract of the equation, n times sigma xy. But then if you look over to the right-hand side on the bottom part of the screen, you'll see that I put the 7. So where the n went, I put the 7. And you see where it says sigma xy on the top floor. Okay, so you see it says n times sigma xy. Well, what's sigma xy? Well, look above. Look right above there. Xy at the bottom of the xy column is 3,413. Well, there it is. 7 times 3,413. I basically just followed the recipe here. It's not a real shocking surprise. And now that I've created that that graph above me, or this chart above me with all the values, I'm just plugging them in. It's really not hard. So again, if we look at the bottom floor, notice the first part of the bottom floor, n times sigma x squared, subtract sigma x, pause, squared. Okay, so now let's look at where I put the numbers in on the bottom floor under the square root sign. 7 times, okay, sigma x squared, well, let's look up on the chart. Sigma x squared is 35,291. There it is. So 7 times 35,291. Subtract, and then it says in parentheses, sigma x, pause, squared. So I put in, let's see, what was sigma x? 477. So I plug that in there, and I know that that's going to be squared. So you can see what I've done here. I've just basically put books on shelves. This is not hard. It's just not hard. The hard work's already been done in terms of getting the calculations. Now it's plugging things in and then just doing a couple more calculations, and then we end up with a single number, which you already know is going to be a decimal, and it's going to be positive or negative, and it's going to tell us exactly what you expect. It's going to tell us the direction at which these variables are traveling and the strength of them. So let's go through it. Okay, so here's my values again from the top. The 7 times 3,413. Okay, when we kind of boil these down, you can see that as I'm going in successive rows down, all I'm doing is the calculations. So between the first row and the second row, all I did was multiplied on the top floor 7 times 3,413. And then I multiplied on the right side of the minus sign on the top floor 477 times 47. So if you look at the second example down, you see that after I've multiplied, I have 23,891 subtract 22,419. Okay, and I've done the similar type of operations on the bottom floor, but I left that square root in place because I can't forget that. I cannot forget to do the square root after I've done all the calculations below it. Many students on tests forget to do that, and I encourage them not to, but I just have to keep reminding them so that they get it in their heads that this is a habit that we need to have. All right, so then once I've subtracted the values from the middle row down, then on the bottom, I see that I've reduced everything down to nearly a fraction. That's, pretty manageable. 1,472 as a numerator, and then the square root of 19,508 times 346 on the bottom, or the denominator. Well, if you followed everything I did, we can just go ahead and do the next slide, and it's predictably, after we multiply the values in the denominator underneath the square root sign, we have a pretty large number, 6,749,768. Okay, seems unmanageable until we hit that square root sign, and now look, in the middle, it's just a fraction. And in fact, it's a fraction you probably already recognize to some extent. Just take a look at the first digits in the middle fraction. See, 1,472 divided by 2,598. Well, subtract, just get in your mind, cancel out the final 3 digits, and what do you see as the first 2 digits? 1 over 2. 1 over 2. Well, what's 1 divided by 2? 1 divided by 2 is 0.5, isn't it? Well, let's look at the R. The R value, the calculated Pearson's R value, is 0.57. So wasn't too far off, was it? It wasn't too far off at all. So you see that we have a Pearson's R value, which is predictably in a decimal form because we're dealing with a fraction here. And I highlighted it for you. It's 0.57. So that's telling us two things. We're learning that it is a positive number, and the relationship between the variables is 0.57. So it's kind of spread out a bit. All right. Well, let's look at the next slide. Now, take a look. This is the same thing you saw earlier. High temperatures, traffic accidents. Okay. Now you know the answer to the question. First of all, you know that when you look at the answer choices, you can right away get rid of C. C is a bogus answer because it's above 1, either negative or positive. See, so when C was 1.54, we know, well, the highest you can go either way, positive or negative, in a correlation analysis is 1.0. So 1.54 makes no sense here. Get rid of it. So we just cancel. We're left with 3. Well, after we did all of our math, we found what? A value. The value was positive 0.57. So clearly the correct answer for this equation, for this example rather, is D. It's 0.57. Okay? So now what's next? Well, we got to find a critical value. We have the calculated value. The calculated value was after we did all the math. Now we got to find this. We need to find a statistical significance, and we do that by comparing the calculated Pearson's R value, with a critical value. And how do we find the critical value? Well, we have to determine the degrees of freedom. Well, how do you do that? Well, I'll tell you. Well, for the correlation coefficient equation, the Pearson's R, the degrees of freedom are determined by the formula n, which is the set of pairs, as you know, minus 2. So once the value of the degrees of freedom is determined, it is used to locate a row on a chart of critical values, just like you did with chi-squared and with the t-tests. Take a look at this one. For the example above, we know that there were 7 pairs. So clearly, the degrees of freedom is going to be indicated by n minus 2. Well, how many pairs were there? 7. Minus 2, it's going to give us degrees of freedom as 5. So you might be asking, okay, we found a degree, for this set of data, we found a degrees of freedom of 5. So what do we do with that 5? We look on a chart. For social sciences, you already know that the default position is usually going to be a p-value of 0.05. Well, okay, so take a look. On the chart on the left, on the left-hand side of this chart, you see at the top it says df n minus 2. Well, we know what our df n minus 2 is. It's going to be 5 because the number of pairs we had was 7. And 7 minus 2 is 5. So we would put our finger on the df and then move down to 5. Okay? You can do that on the screen if you want. Move down to 5. Then we move across to the 0.05 value. So when we see the intersection of where the 5 is on the left and the 0.05 is in the first column, in the second column, you see it's 0.755. So we have the critical value for this particular degree of freedom. So this is what we're going to calculate. This is what we're going to compare and contrast. Let me go to the next slide. So the calculated Pearson's R, if we did all of our math, is 0.57. The critical value, once we looked on the chart, is 0.755. Which one's larger? Well, clearly the critical value. Because the critical value is greater than the calculated value, we find no statistical significance. We must accept the null hypothesis. And as I stated at the beginning of this presentation, the null hypothesis is for correlation coefficients going to state there is no relationship between the variables we're looking at. So, because we found a calculated value, 0.57, which was less than the critical value, 0.755, we must accept the null hypothesis. Now, when we're researchers, a lot of times we're cheering for the null hypothesis to go down. But to be absolutely honest, candid, and ethical, we need to honor the numbers. And when we find that the calculated value is lower than the critical value, then we have to say, well, we accept the null hypothesis, and that's just that. I mean, we're sad, but is what it is. So that is that for doing things manually. I showed you how to walk through all of the equations and get to the calculated R value. Then I showed you how to get the critical value from the chart after determining the degrees of freedom. And then once we've made the comparison, you know whether or not you found statistical significance, and based on that, whether or not you're going to accept or reject the null hypothesis. Now, I had promised at the beginning that I was going to show you how to do things from the perspective of Excel as well. And now I'm going to do that. And now we have, as promised, the same variables before when we looked at them in the PowerPoint presentation in the context of the Excel spreadsheets. So let's take a look at what I have here. You see that for the X column in the top left, we have all of those heat values. Again, these are temperature values. Remember, 91, 56, 75. And then in the Y column, we have the number of accidents. So all I've done is just transposed all of the data from the example we were looking at in the PowerPoint presentation onto the Excel format. So really not a whole lot of work here, just basically move the values over. Once I've done that, I'm going to go ahead and select any kind of any cell, not the numbers. And with Excel, the magic key is equal sign. Equal sign is what basically gives a command to the computer to select a function for whatever you're going to do. So we did in the PowerPoint presentation Pearson's R. So not surprisingly, in the Excel portion, we're also going to be doing Pearson's R. So in order to get Pearson's R, all I have to do on Excel is hit the equal sign, then I hit P. Now look at this. I all of a sudden have a little drop-down menu that just appeared. And not surprisingly, there's a value here, or rather a menu here, an item here on the menu called Pearson's. And there it is. So I'm just going to hit that. I'm going to hit it twice. And now look at that. It gives me equals Pearson, all in caps, and it gives me a parenthesis open. And then it says, kind of in terms of directions, array 1 and array 2. Well, it's prompting me to select the numbers I want as the first array, which really is the first set of variables. So I'm going to go up here to 91. I'm going to hold down the left key, or the left side of my mouse, and I'm going to go down all the way to 98. Now look at that. As I'm doing that, the numbers are filling in automatically right here. Okay. If I want to go ahead and lock that in as my array, I just simply hit the comma. Once I do, notice that there's a solid border around these numbers. Now the computer's waiting for me to put in the second array, which will be, of course, in this case, the Y values. So again, just like I did with the X, I start at that top cell, 7, which is the first value. I hold down the left side of the mouse, and I go all the way down to the 8, and this time I go ahead and hit shift and close. Now look, it locked both sides in. So both of these values, starting with 91 to 98 on the X column, and beginning with 7 and ending in 8 on the Y side, they've all been captured in these parentheses. And again, because I know it's equal Pearson, I know that we're going to be doing a Pearson's R analysis just like we did by hand on the PowerPoint presentation. So now that I've got one simple step left to do, I simply hit return or enter. Oh my gosh, there it is. Remember what the value was in the PowerPoint presentation? It was positive 0.57. Well, it gave me a value here on Excel that if I round up to the second place after the decimal, it's going to be 0.57. So again, I got the same thing that I got from the PowerPoint presentation when I did things manually. I just did it much faster with Excel, but now I know exactly what that number means and where it comes from. Well, this computer, my Excel, program, did all of the calculations that I just did by hand in the PowerPoint. So now we know what this number actually means. Okay, now we have a greater appreciation and understanding of what this R value is. And a lot of times what you can do here is just go R equals, and that just lets you know that this value here is a Pearson's R. Now, there's some other things you can do that are kind of fun with these numbers that you can kind of get a little more information out of your data set. Let me show you. If I go ahead and highlight both the X and the Y columns, and I stop right there, then I move up to the Insert tab. and then click on it, I'm going to pull up a new screen with a new set of options and functions. If I move from left to right all the way over to where it says recommended charts to charts, I see right here, you can see my cursor moving, where it says insert scatter. Well, what's that sound like? Scatter plot? Should. If I go ahead and click on that little downward facing arrow and I select the very first scatter and then hit up, there it goes. Look at that. It gave me the plots of these values. Look at that. A nice little chart. Now, if I want to take this a step further, what I can do is I can go to any one of these points and then I can right click and look what I have here. I have a new menu and it gives me a number of options, but the one that I'm most interested in this is called the trend line. So I hit trend line and now all of a sudden it's going to give me a line that shows best fit for these variables. Now you can see right here, kind of like we did earlier when we were looking at those different examples in the PowerPoint, we saw a flow of the numbers. You can see that loosely the flow of the numbers here is from left to right, kind of going upward, but it's kind of loose. That explains, or rather that's explained by the 0.57. So it's kind of loose. You can kind of see the direction of it, but it's not a perfect line. If the decimal had been closer to 1, this would have been a straighter line and probably would have come along this line. The points of the graph would have been more lined up with this. Now, if we go ahead, and another little trick you can do is with this Format Trend Line menu, go ahead and go down and click the bottom two boxes, and we get some new information. Look at that. If I move that up here, I can see it a little more clearly. And here's something interesting. Remember what we talked about in terms of the equation for correlation coefficients? We said that it's Pearson's R. Well, look at what you have here. R squared. Well, what do you think you would have to do to find R? Well, you have to take the square root of that. So if I want to do that, all I do is I come down here, and I find it helpful to just go plug in the number and then come off to another cell. And this time I'm going to hit that equal sign again, because again that's prompting a function. And then I'm going to hit SQ. It's going to give me square root. So what I'm going to do is I'm going to click on this once, actually click on it twice, and come over to the value in this in particular cell, which of course is the same value we found up here. And when I double click that, it's going to just put that value right in here. If I close parentheses and hit enter, oh, look at that. Nearly the same value is up here. I want to point out something though. Notice that if you're doing a square, it's not going to give you whether it's positive or negative. Because anytime you do something times itself, anytime you square a number, it's going to give you a positive number. So if it had been a negative, it's going to end up positive. And obviously if it's positive, it's going to still remain positive. So you're going to have to look, if you do things this way, at the shape of the line and realize that if this had been going the opposite direction, even though we got a positive 0.566 here, it's going to be a negative because of the direction at which the variables are traveling. The other thing that I need to mention is that we got from this information the Pearson's R calculated value. But we still, if we were trying to do an analysis for statistical significance, we're still going to have to find the critical value. And as you already learned from me earlier in the PowerPoint portion, to find the critical value, we're going to have to take the number of the pairs, which again is 7, minus 2, which would end up giving us 5, and then we would look at that chart. So once we looked at the chart, we would find, of course, the DF on the left, and then move across to the 0.05, which is kind of the default for social sciences, and that would give us the critical value. So there's limitations to this And I think what you're going to find later in SPSS is it's the easiest from the standpoint of finding all of what you need at once. The only problem with SPSS is that if you haven't studied the manual way of doing this, you really don't have a great appreciation or understanding of what all the numbers mean, or what formulas are being kind of calculated in the background before you get the number. You've taken a shorthand, but you may have cut out some of your understanding of the meaning, which is what I'm trying to avoid here. So I hope that this presentation so far has been clear, and in the future what I'm likely going to do is go ahead and add on to the back end of this another section for the SPSS analysis. Okay, thank you.